Section 2.1, representations of integers. Let b be a positive integer which is greater than 1. Every such an integer can be written uniquely in this form, where k is a non-negative integer. Each coefficient here satisfies the following double inequality. Aj is greater or equal to 0 and lesser or equal to b minus 1. Moreover, the initial coefficient is not equal to 0. Corollary: every positive integer may be represented as the sum of distinct powers of 2. Notation: if we write n as this, we use the following notation: ak minus 1 and so on a0, or which is over here in parentheses b. Let me give you the following illustration. 125 can be written as the following: 2 times 7 square plus 3 times 7 plus 6. Note that each of these numbers, 2, 3, and 6, satisfies this double inequality. So AJ's here are 2, 3, and 6. Each of these numbers is greater or equal to 0. Each of these numbers is lesser or equal to b minus 1. Remember, b is 7. Each of these numbers is lesser or equal to 7 minus 1, 6. And now, let us denote this by 2, 3, 6 in parentheses 7. What we see in front of us here is so-called base 7 expansion of 125. Similarly, since 147 is equal to this, and again note that each of these numbers is greater or equal to 0 and lesser or equal to 2 minus 1, which is 1. 147 is equal to 1. And now we have 0, 0, because there is no 2 to 6 power. There is no 2 to 5th power. So coefficients in front of 2 to 6 power and 2 to 5th power are zeros. Then here 1, therefore here 1. There is no 2 cube and 2 square, means coefficients are zeros. And lastly, 1, 1. So what we see in front of us here is so-called base 2 expansion of 147. Big question is, how do we come up with these, or say with this without guessing? We use the division algorithm. Let me show you how we come up with base 2 expansion of 1864 without guessing. Please take a look at this. By the division algorithm, there are unique numbers, Q and R, that satisfy the following. 1864 is equal to 2 times Q plus R. Next step, let us apply the division algorithm again to 932. 932 is 2 times 466, plus 0. We apply the division algorithm again to 466. And the result is 2 times 233 plus 0, and so on. Question is, when do we stop? Answer, we stop when q is equal to 0. Once we hit 0, we stop. Here's what we do next. We come up with these numbers or reading up the remainders. Note that here we start with 1, 1, 1. Indeed, 1, 1, 1. Then we have 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0. It's exactly what is written here. So, according to this, base 2 expansion of 1864 is this one. By the way, what is written here means the following. 1864 is 1 times 2 to 10th power plus 1 times 2 to 9th power plus 1 times 2 to 8th power. Here we have 0. There is no 2 to 7th power. 1 times 2 to 6th power. There is no 2 to 5th or to 4th power. Plus 1 to cube. And then there is nothing here because here we have 0, 0, 0. So big question is why this procedure allows us to come up with the following representation of 1864 with the representation. Well, let me give you the following explanation. Please take a look at this. We start from the bottom. According to what is written here, and I copy it here, since 2 times 0 is 0, 1 is equal to 1, which can be written as 1 base 2. 1 base 10 is equal to 1 base 2. Next line. 3 is equal to this. Here is what we do next. Note that 2 is equal to 2 to first power. And what is written here, according to our discussion, is equal to 1, 1 base 2. So 3 base 10 is equal to 1, 1 base 2. And indeed, in order to come up with this expansion, we just read remainders up. 1, 1. Keep going. 7, according to what is written here, is 2 times 3 plus 1. Now, let us replace this 3 by this expression, because 3 is equal to this. So, we replace 3 by this, done. And now, let us expand parentheses, done. Note that again, according to what is written here, this is equal to 1, 1, 1 in parentheses base 2. And indeed, in order to come up with this, we just read remainders up. 1, 1, 1. Next, 14, according to what is written here, is 2 times 7 plus 0. But 7, which is over here, is equal to this. So let us replace 7 by this. Done. Let us expand parentheses. And again, according to what is written here, this is equal to 1, 1, 1, 0, which is exactly what is written here, base 2. And again, short way to come up with this is the following. We read remainders up, 1, 1, 1, 0. 29, according to this, is 2 times 14 plus 1. Or replace 14, which is over here, by this. Done. Expand parentheses, which gives us the following. 29 base 10 is 1, 1, 1, 0, 1 base 2. We just put together these coefficients. But according to what is written here, there is a faster way to come up with this number. Just read remainders up. 1, 1, 1, 0, 1, and so on. Next. Now let us find base -2 expansion of 1864. Well, we apply totally same procedure. We apply the division algorithm successively. 1864 is equal to -2 times -932 plus 0. Now we apply the division algorithm to this number, done, and then to 466, done, -233, done, and so on. We stop when we obtain 0 here, when the quotient is 0. Conclusion. 1864 base 10 is equal to this base -2. Lastly, let us find base -2 expansion of -1864. Again, we apply the division algorithm successively and read remainders up. This is equal to this, 1, 0, 0, 1, and so on, 1, 0, 0, 1, and so on. Folks, questions here?
Is there an easy way to switch between a base and its negative?
No, that's the whole point. So your question is, here we just switch signs. Does this necessarily mean that here we switch signs? The answer is no, because over here, all digits are positive. So there is no easy way to switch from this to this or from this to this. These are pretty different sequences of ones and zeros.
Okay.
But here is the next question. Over here, we have 3 examples. 2 examples for positive 1864, base 2 and base -2, and 1 example for negative 1864, base -2. The natural question is, how about base +2 expansion of -1864? Can we apply same procedure? Well, guys, the answer is no. If we want to find base 2 expansion of -1864, we just put negative over here. Please take a look at this. On the left-hand side, we have negative 1864. This is equal to negative, and then we just copy this over here, base 2. So we do not use the division algorithm in order to come up with base 2 expansion of negative 1864. Step 1, we find base 2 expansion of positive 1864. Done. And then we put negative in front. Question is, why all of a sudden, in this case, we do not use the division algorithm? Well, guys, first of all, please take a look once again at this. What is written here means the following. 1864 is 1 times 2 to 10th power plus 1 times 2 to 9th power plus and so on. Note that if instead of 1864 we have negative 1864, there is no way we come up with this, because 2 is positive and all a k's are positive. According to this, we cannot write negative number as a combination of positive numbers. So, according to what is written here, negative 1864 is negative in front of this expression. But then the next question is, how come that in this case we can't use the division algorithm? What if we apply the division algorithm in this case? What will go wrong? Well, here is an illustration. Please take a look at a simplified version of that example. Let us apply the division algorithm in order to find base 2 expansion of negative 7. Once again, according to this remark, we don't use the division algorithm if base is positive and the number is negative. But let us try, let us see what will happen. So, by the division algorithm, negative 7 is 2 times negative 4 plus 1. Negative 4, which is over here, is 2 times negative 2 plus 0. Negative 2 is equal to 2 times negative 1 plus 0. Negative 1 is equal to 2, and now, please take a look. Over here, we get negative 1 again. Since over here we get negative 1 again, there is no way we can obtain 0. Remember, I said we stop when we get 0. Over here, there is no way we can stop at all. Here we get same as here. We put negative 1 here, yet again same expression, and so on. This is the reason why, if the number is negative but the base is positive, we do not use the division algorithm in order to get the expansion. We instead first consider the corresponding positive number, find base B expansion, and then attach minus in front of the whole thing. Any questions here?
Can you repeat what the general rule of not using the division algorithm is?
So the general rule is, if the number is negative, but the base is positive, we do not use the division algorithm. Instead, first, we replace our number by the corresponding positive number, find base B expansion, and then attach negative sign.
Thank you.
Next, often in applications, we use base 8 or base 16 expansions. Now, in base 16 hexadecimal notation, there are 16 digits. Usually, we denote these digits by 10 digits from 0 to 9, and then the letters A, B, C, D, E, F. Example, convert this from hexadecimal to decimal notation. Well, here's how we do it. A represents 10, B represents 11, and so on. F represents 15. We start from A. 10 times 16 to 5th power. Why 5th power? Position number 0, number 1, number 2, number 3, number 4, number 5. So this is position number 0. Therefore, this is position number 5. We raise 16 to 5th power. Plus 3, which is over here, times 16 to 4th power. Plus 5, which is over here, times 16 cube, plus 11, because here we have B. We replace B by 11, times 16 square, plus 0, plus 15, because F stands for 15. And then we compute the whole thing. We get this number, base 10. Last but, a simple conversion is possible between binary and hexadecimal notation. Here's how we do it. First, let us convert hexadecimal to binary. We use this table. We replace 2, which is over here, by 0, 0, 1, 0. However, we skip 2 initial zeros. We start from 10. So we replace 2 by 10. Next, F. We replace F by 1, 1, 1, 1. We attach 1, 1, 1, 1. Next, we replace B, which is over here, by 1, 0, 1, 1. 1, 0, 1, 1. And lastly, we replace 3, which is over here, by 0, 0, 1, 1. Now, we do not skip the initial zeros. Note that since 2 is on the first position, we skip zeros. Over here, for 3, we use all 4 digits, 0, 0, 1, 1. Now, to convert from binary to hex, we start from binary. Next step, we break this into blocks of 4, starting from the right, not from the left, from the right. Block of 4, done. Block of 4, done. Block of 4, done. But now over here we have only 2 digits. Since instead of 4 we have only 2, we put two initial zeros to create block of 4 again. And then we replace this by 3, this by D, this by E, and this by 9. Done.